Okay, so this is lecture 16, and we were looking at building blocks of PLL, and we will continue our discussion on phase frequency detector. And we saw one kind of phase frequency detector, which was NAND gate, NAND based PFD, and we found that you have, because of the finite t reset time, you have a region in the PFD gain characteristics which was negative, and which actually leads to a limit the frequency of operation of PFD. So if the ideal characteristics of PFD are like this, then for a NAND based PFD it was like this, and this region depend on your T reset time. Okay, so the next thing is you look for other architectures which can give you a lesser T reset time, and in this case T reset time was, in the first one it was T NAND 4 plus 2 T NAND 2 plus tau D. That was the reset time. So the next one is based on fast transistor logic, transistor PFD. So let me just pull up the schematic for that. Let's see, which was fast transistor PFD. Okay, so now this is the problem. You can't see anything on this, right? It's too small. So, okay, use the draw. Yeah, this is the problem here. Sorry, use draw. So let me just zoom this one little bit. Okay, so yeah, now you can see that. Okay, so in this pass transistor logic, we means the first one, I would say that this one is just a D flip-flop made from a pass transistor logic, right? I'm using the same logic to implement the PFD here. Okay, so in this case, your up and so this is when your R is equal. So this is higher, like active high. Okay, your when R is 0. So let me just zoom out a little bit. Your R is 0. Sorry, I'm speaking R0 and plotting it high. So you have R equals to 0 and V equals to 0. At that time, in this case, you see that this PMOS will pull up this node on both the cases. Okay, and your reset bar is actually high. That means because reset bar is the first signal here. Reset bar, this signal is high. Sorry, reset bar is low as such, not high. Reset bar is when reset bar goes, so this up and down are actually, wait, up and down signal both are actually low. Okay, both are low. If your up and down signal both are equal to low, your reset bar signal is high. Okay, so reset bar signal is high, and that time reset is low. So if reset is low, this transistor is cut off. Both of them are off. Okay, now look at this. When R goes from when R goes from 0 to high, okay, at that time what happens is, so it means actually before your reset signal goes to low, at that time this node is actually pulled to ground. So the inverter output node is actually VDD. Is pulled to ground, not pulled to ground. When R is equals to 0, then sorry. When R is equals to 0, at that time PMOS pulls this node to VDD. Okay. Huh? Reset is, this is the reset signal, right? It is written as uh, this is reset signal, this is reset bar. Pardon? This one. Okay. So what happens is when your R is low, this is a PMOS transistor, this is actually high. This one is ground. Okay. And that time as R goes from 0 to high, this node is pulled to 0. This is node pulled to 0, up goes high. Okay. And for the NAND gate, nothing will change unless both the signal actually becomes 1. So when V goes high again, V goes from 0 to 1, at that time down will go high, and then your reset will change, and as soon as the reset changes, it will pull this node up to VDD. This is a closer path, and when this pulls to VDD, up and down both goes to 0 again. Okay, so in this case your reset, T reset is actually equals to 2 times NAND plus T inverter delay. In the previous case, it used to be like when we tried to have a large, like not larger, there was a T NAND 4 gate which was having a larger input to output delay. So this particular PFD, actually has a lesser glitch or lesser glitch time as compared to the NAND based PFD. Yeah. R is for right. Whenever R goes from right, whenever R goes high, right. So mhm. No one is holding it. No, so okay. So again, this is again the case where means if the leakage starts happening, if no one is holding and the leakage starts happening, this will have a problem. Okay, but if the leakage is not substantial in the time which you are considering, then the gate voltage will not. Gate voltage is not a problem. So in all the past transistor logic, this will be some kind of issue or the other. So means in comparison to this, you can say the NAND based logic, whatever the NAND based circuit we saw in the previous lecture, that has no issues at all. Means holding it or because it's always tied to VDD and ground, and the potentials are always fixed. So all these, so like it may seem tempting that in order to get a better characteristics of the PFD or have a like, so for this past transistor based PFD, you may have something like this. You can get a better characteristics. But then whatever you are saying, this past transistor logic will have those issue whether the voltage is hold or not. Whereas the NAND based logic, whatever characteristics have, it's pretty robust in that sense. Okay. Pardon? Yeah. So when you are operating at a higher frequency, in that case, you do not have much time for even to discharge. Okay. But when you are operating at a lower frequency and you need to exercise whole range, then this will be an issue. Okay. Then the third kind of, sorry, this one. Okay. The third kind of PFT is based on glitch. So even in this kind of PFD, the past transistor PFD, the problem with the missing the edge, problem of missing the edge is still there. Okay, this only thing is because the reset time has reduced, so your mean missing edge not the probability, but missing edge a region has been reduced here. Okay, so then there is another one which is glitch latch based PFT. So this is based on a glitch latch based flip flop, which is actually halfway between the edge triggered and halfway between like being a transparent. So if you have any flip flop which is edge triggered, which means that as soon whatever the data is present just before the edge or the edge, that data is translated at the output. That's a flip flop, right? Edge triggered flip flop. The other thing is a latch, which means when the clock is high, then latch is transparent from input to the output. Okay. Now this glitchless based PFD is based on glitch latch flip flop, which is actually a halfway between your latch and a S trigger flip flop. So let me just show that one, which is this. Okay. So in this case, let me plot the input versus output characteristic. So let's say when clock is low, when clock is low, at that time your X node is pulled to VDD, right? And X node is VDD and Q is actually 0. So this is the case when they are low. Okay. And it doesn't matter what D is. But the thing is, the in between potential, this will be pulled to ground. There's an inversion in the clock. Okay. Now, what happens is when you're, so let me just say the data can be anything high or low. So let's say that the data goes high after some point when the clock goes high. Okay. So when the clock goes high, X doesn't change until D goes high. Once D goes high, your X drops to 0, right? And this is again depending also, it's like this. So when the clock goes high, then there is CKD also, right? CKD. So after a certain delay, your clock delay part will actually go low. It was initially high and that will go low. Sorry, this is slightly away. So let me just mark this. So what happens? This is D, right? So as D goes high, your X goes low, and as soon as your X goes low, your Q will change the output. Okay. Otherwise, it remains the same. So we are just looking for the change here. Now, once your clock goes low, at that time, you cannot change the output, right? It is always means whatever you have sampled, that is the output. Now, when clock actually goes low, the whole thing is here. When clock goes low, at that time X is pulled to VDD, no matter. Okay, it can be this. X pulled to VDD means Q goes to 0. So this part of the operation, actually your output is not valid mode at the output. You see that it is edge triggered in the sense that during the rising edge of the clock, you sample the data, whatever it is, and then it is valid only for a half the period. Okay. So this flip flop makes a way for means it's an improvement over all other PFDs. So let me just represent this. Insert picture. glitchless PF. Oh man, this one is, why is it coming here? This is a serious problem. Wait a minute. Let me just give you the final result for this, which is, we will look at this in more detail just next class. Let's see why I'm not getting this part. So what happens is that this particular flip flop has a characteristics of flat region for a while, and then this also has the negative portion like this. This is the glitch latch based PFD. Okay, and the reason for getting that particular okay, let's try it if possible. Okay, so I have R because R V. So what I am saying is R is low and V is low. At that time when R is low, your GR pulse is considered and your reset bar is actually high. Okay, and your up slash down both are actually 0. Okay, up and down both are actually 0, which means that this is 1 and this one is 0 and this is 1. Okay, so that thing holds. Now you can say what this GR will be. This GR will be a higher potential because the bottom, this NMOS transistor is actually off. Okay, now when your R signal goes high in this region, then what happens? You pull the GR node to ground. So GR node was pulled to ground as such, right? And when GR node was pulled to ground, this node is pulled to the ground. So very much this is a case where you are working on hold voltages and pushing and pulling are done with the hold voltages, right? So whether it is pulled to ground or pulled to VTH or something, that's a different thing. So when your input of this up inverter is pulled to ground, your up goes high. Okay. Now the same thing and nothing else changes because still the reset bar is still 1 because one of the signals is still, you are having this one goes ground, which is this is 1. Wait a minute. Okay, yeah. So what did I do here? So what happens when this node potential goes to 0, this goes to 1, and this was already 0, so you still are reset bar is still 1. Okay, now when V goes high, the same thing happens. So V goes high after some delay. The same thing happens, and now let me just see. Okay, there is another thing with this R signal. There will be a delayed clock here. Okay, so when you have a delayed clock, what will happen when this goes to high? This will get cut off. Bottom transistor gets cut off, and then you cannot entertain any changes in the up signal. Okay, now so what? Okay, the other thing is when bottom transistor gets cut off, what will happen to GR? It will rise to some potential. Okay, so this is with the delay, with respect to that whatever the delay is. I do not know what the delay can be, but whatever the delay is, it will go to some higher potential, or it can still remain ground. Let me just keep it to ground only right now. Okay, where now when V comes, the same thing happens, and your down goes to high. Here, when both up and down goes to high, that means both of them goes to 1, and T reset bar goes to 0. As soon as this goes to 0, your PMOS will pull these nodes to VDD, and your up and down both will come down after a while. Okay, now this is what happens when I'm showing you the phase error difference here as such, right? Now what happens, what is this? Oh man, undo, okay. Okay, so now the other one which I am trying to tell you is, let's say this is your R signal, and the V signal, as we have seen the previous cases, that the V signal goes high at a very narrow, very close to your 2 pi signal. This is R, this is V. Okay, now the question is whether your this edge will be taken into account or not. Okay, so is everything seems so far right? Now the thing is that this goes slow till the time you are having this T pulse period. So let me, this is crazy. So this, let me just pick up another. So when R goes high, your GR goes low, and there is some pulse T pulse period itself, which is basically the pulse should not be like exactly like this. So let me just say that it goes high at a separate, and this period, which is decided by the inverter delay, this is the pulse period in which your this latch is still active. Okay, so let's say the delay which you are getting, okay, in this case, so what will happen in here, your up pulse will go high at some time, and that will remain high till the time your V signal, V high comes, and then finally it gets reset to 0, where your down will also do something similar. Okay, whereas your reset signal, so I didn't plot the reset signal here, your reset signal, reset bar can be something like this. Okay, that can happen, but if your the same period which I am writing here, which is a T pulse period, if your reset is exceeding that time, where the next pulse is still means you can still, this part is still active, which is, let me just move this. This one can still take the next rising edge. Okay, so this can still take that rising edge as such, and you will not miss the, like the rising edge that you were missing earlier because your reset signal was there. Okay, I think if you work this out with waveforms, this will help me. Looking at just the waveform doesn't help that much. But the thing is, if your reset signal So this is again dependent on your T pulse and T reset. If your rising edge is coming or your glitch is coming after this T reset, then you cannot do anything, and then that is gone. Okay. So if you move within a certain time within the T pulse, that is where I told that I get some kind of flat region. So let me just plot in a okay. Uh, yeah. So for if regular PFD characteristics are like this, and NAND based characteristics are, or you can say pass transistor characteristics are something this, then your glitchless PFD characteristics will be some flat and then they will be here. And this flat region is dependent on the T pulse period. Okay. So, but this is again dependent on your all your past transistor logic. So leakage and other things will be important for the frequency which you are considering. And in no way you can remove that delta means other than t pulse equals to some very specific value, you will have a flat region coming to zero and going back. Okay. So these are the three standard phase frequency detectors which are used, and you can figure out what suits best for your design depending on frequency, power, and all. And surely this one is the NAND gate thing because it is using the full-fledged NAND gates, so they will be having more power consumption, and mostly I think they will be slower. Okay. So the other thing in this kind of circuits, you see that I have used a NAND gate for reset here, and similarly a NAND gate for reset here. So there is for the schema for the design of NAND gate, your input to output delay should not depend, because this is a symmetric between R and V, right? So whether R comes first or V comes first, the delay from input to the whichever is triggering it, the delay from input to the output should be same. Okay, so for the NAND gate design, if let me see if I'm making it the right NAND gate for a long time. So let me just say if I have something as A, B, A, and P, right? And I'm looking for A to Q or B to Q output. In this case, T delay for A to Q will not be equals to T delay from B to Q, because they both are having a different parasitics to charge and discharge. So mostly we want to have a symmetric delay, so we use symmetric NAND gate design, which is okay. So A, B, P, A, and A, B. I would say in any kind of logic, whether it's an AND gate or XOR gate, or when you are using for a XOR phase detector, right? You should look for the input to output delay should not means if you're looking for any symmetry thing, then you should look for the input to output delays and they should not differ. So since we are just talking, so let me just show you for an XOR gate, right? You have, or let me just plot it at X naught. So this is A, B, and Q, right? And XNOR gate is, so I have, Okay, so this will be a b, a bar, b bar, and you have a b bar, and I can say a bar b, right? This will give you the XOR operation. Okay, but the problem with this in this thing is the same, that your A to B, A to Q transition and B to Q transition will not be the same. So what you do is nothing much, but just, okay, I'm not able to click on this. Oh man. Okay, just remove that part. So what you do, you just make a copy of this and give, if you want something to be fully symmetric, you do this thing also. B bar A, sorry, and this may not matter to you when you are doing a low frequency thing, but this matters a lot when you are doing a high frequency stuff. Similarly, you do for the bottom. Okay. Any logic gates which you are going to use in high speed design. So B A, B bar A bar. Okay. So that concludes the your PFD design. Any questions so far? Is it too sleepy or something? Oh, okay. So, okay, the important point is, so let me just show you by an example. So let's say, did you get the AND gate one or no? You get the NAND gate one, right? The same is for XOR. So if I had only this, let me just say this block, right? So let me give you a thing. So when, okay, this is a XOR gate. So when A and B both are high, right? So let me just give you a difference. Consider this case A and B. Okay, when A and B both are low, okay, at that time your Q output, A and B both are low, was high. Sorry, low, not high. Right? Then when A goes high, what happens? So think this way: when B is low, that means your B. When A is low, you're actually A bar is high, and this B is active. Okay. So look at which signal will make the transition to the output. So we know that when A is high and B is low, the output should go high here, right? Let me not extend to the other point. Go high here. So which switch is triggering that output? So that is when B is low, this MOSFET is active, whereas A was low, but this control is A bar, so this is off, right? And in the other case, every other transistor is every other branch is actually off. This one is off, right? And A and B both are low. So this is actually A and B both are low, means this branch is active as such, right? Now what happens as your A goes high, this transistor get active and this transistor deactivates. So the transition to the output is being triggered by A, right? This A and this whole branch conducts, but it is triggered by it, which is connected to VDD. Okay, now I just reverse the signals and I say that first B goes high rather than A goes high. Okay, So in that case, which signal will trigger? So let me just say, in that case, this MOSFET will trigger the output to VDD. So think about it. In one case, I have to conduct from here to here, and actually means when this was off, then I have to actually, this is pulled to whatever potential it is, and then you conduct from here to here, right? In the other case, when A was low, at that point, this was already like pulled to VDD, and I'm only doing this. So the thing is, the transient sequence changes. Because of that, the delay from the input, whatever A or B signal is, to the output can change. So if in place of that, I have the symmetric part also. So in one case, if the bottom transistor is means for B signal, both the bottom and the top transistor is triggering this case. So you will see the same whether A comes first or B comes first. So you need to use this symmetric logic if you are worried about this input to output delays. Okay. Is it going to be faster then? Now what? Now the question will be this: when you say this is going, so in the only one case, one transition will be faster, other will be slower. And my hope will be that when you do a symmetric thing, both the edges may lie in between. So the thing is that you are adding more, whether I think that may depend on the design of means how you lay and do other things out. But this will not be the slower than the slower edge of the first one. So you see, right? Means in this case, one edge will be slower, other is faster. Okay, but in that case, when you combine the symmetric, it cannot be slower than the slower one. And the other thing is both edges will be actually the same. And I think if it is done more properly, design and layout, you may get it like it is close to the faster edge only. It is putting more load on the, not necessary. So why would I basically go and put a means if I have an X circuit, why would I only always do X and X? I can do X by 2 and X by 2. So whether it is going to put a more load on the previous stage, that actually depends on how you do it. Now you are connecting, now the whole question is you may have more intermediate nodes, but those intermediate nodes are also having a lesser capacitance. But if you lay out capacitance, so let me just give you an example. If this is of size X and you have a certain parasitic capacitance, you broke this thing in X by 2 and X by 2. Okay, but your parasitic capacitance at each intermediate node still remains the same. CP1. So I am distinguishing between this. I have only, let's say on the first part, and I have CP1 here. When I break, when it was X, then the intermediate node was CP1. So when I break into X by 2 and X by 2, the CP, if you still maintain the CP1 and CP1 at both the nodes, then I think it will be slower. So this is comes to the layout. Okay. So I think the other part next one I will go for the charge pump thing tomorrow. Sorry, in the next. There is still time, right? Okay, let's stop. That will be a whole section. Let's stop here and we will look for the charge pump